All right, why don't we have a look here? So we doing okay with 7.1? Any questions? I mean, and
First page is pretty straightforward.
yeah, I think so. If I give you a hint on the first page, it's, when people have problems with this stuff is when they make it too complicated. This depth times 0.433 gets you pressure. That's it. Okay. And how the stuff's connected together, if it's connected at an angle, or if the container's an odd shape, or if the container's big, or if the container's small, doesn't make any difference. It's just depth goes to pressure. That's all there is to it. Okay. We're doing all right with that? Okay. So that goes for 1. Now 2, what we're doing there, those are elevations is what they are. Okay, so, and I'll use this in the class. So when it says L equals, that means the elevation, that's generally above sea level is what that is. So, that would be a tank there going down to a hydrant, and you'd know the elevations above sea level of those points. So if you subtract them, you'll get the height. Okay. Okay, then number 3 there, you need just to use the height and then factor in the specific gravity. Okay, number 4, you have to figure in the specific gravity as well. So I would probably just find the water pressure A first, and then just take that and multiply it by the different specific gravities. And y'all know the specific gravity of mercury? Yeah, 13.6, yeah. Okay, so, yeah, so the specific gravity of mercury is 13.6. Right. And then, okay, now this next one here, we've got pressure readings. So are we good on 7.5? Because you know that 1 psi is equal to 2.31 feet. So what you'd want to do there is convert those pressures into elevations. Okay? And that's how, if you're, I don't know, if you worked this summer and you had a water tank, let's say that you kept an eye on, and there was a computer console that had a readout of the volume of the tank, probably how that worked was there was a pressure transducer in the tank and that reads the pressure, and then there's a little logic routine in there that converts that into height. Is probably the first step on how a little device like that would work, okay? So you're just going to take the pressures there, convert them into heights, and then probably take the difference in the heights, okay? So we got any question on that? Okay, let's just see something here. So for instance, this 14 psi, I got 32 point, I took it out a little ways, so 32.34 feet is what I got for that. Okay. All right, so that's 5. 6, pressure in a city water system is 72 psi. How high above the water system could a building be constructed if the static water pressure cannot drop below 20 psi? So basically what we're saying here is if you have a water pipe, that's at 72 psi. And then we've got a building up here that, the pipe feeds into, let's say, kind of like that. And so, I'm a little bit out of scale here, but here's the building, okay? And this is 20 psi. So that's a very similar problem to what we have right there. Just look at what the equivalent heights are of the 2 pressure gauges, and you should be able to work out what the elevation difference can be. Or you could subtract off the pressures and convert that into elevation, something like that. Okay. Good with that?
Do larger high-rises have like booster pumps then?
Yeah, I think they do. They'd have to, like, I don't know how high, you know, like 10 feet per story or something like that, something roughly.
Yeah.
And then they have a water tank maybe up at the top.
Yeah, I've heard of, there might be water tanks at the top. And that would probably make the most sense, is just to have maybe a booster pump that, probably a pressure tank, and then kick it up to maybe a tank on top of the building perhaps. I don't know quite how that would work. But I think each, like a skyscraper like that, would have its own water system that ties into the city system. And there'd be some sort of backflow prevention on that and that sort of thing. Okay. But I don't really know, you know, exactly how something like that would work, but I suspect that's, you know, kind of the deal with that. All right, so this one here, this next one, 7.7, what you would do is you would take that 42 psi. See, that's what's required to push the air out of that tube, is you've got to generate 42 psi. Now, when you're looking at air pressure, it's not like water where there's a huge change in pressure for, in this case, 234 feet of elevation. It's not like there's any sort of relationship like that. If that gauge reads 42 psi at the top, air is so light that there probably is a pressure pretty darn close to 42 psi down at the bottom too, okay? It's different than water, okay? So you're assuming that that pressure gauge is telling you the pressure that's required to push the water out, okay? Now you can convert that into feet of water is what you can do, okay? And that will tell you how much water is sitting on top of that tube. And that's about 97 feet, I think. So when you run the numbers on that, you ought to come up with 97 feet. And then once you've got that, you know that that's 97 feet. You know that the total is 234. So you should be able to figure out the depth of the well having those two numbers. Okay. So you read the pressure, that tells you how hard it is to push the air out of the bottom of the tube. Then you convert that into a height. And then if you know that tube is 234 feet deep, you can figure out how much is left over for the depth of the well. So the depth of the well starts usually at the ground surface and measures down. Okay. So we got questions on that? Doing okay? Yeah. Adding them? No, I think it'd be subtracting, or for this one. Yeah, because see, you got 234 total. You use up 97, so it's just a subtraction. So yeah, it'd be a difference. It's a subtraction. Okay. All right, so the next one here we've got is, the idea here is you're going to take the face of the gauge and change it. You know, you might do it in a little fancier way than a Post-it note, but that's the idea there. You're going to put a new gauge face on there. And what you want to do is change the pressure reading into a volume reading in gallons. Okay? So you want someone to be able to look at that gauge with the moving dial and look at it and go, okay, the volume of the tank is such and such, okay? And this is, you know, there's a series of steps here to get this done, okay? But you can take the pressure reading at the bottom of the tank and then from that determine the volume. Okay? Now the key step here is just to get pressure into feet, right, of water. Because if you know the height of the water in that tank, you can figure out the volume.
So if that's the tank, and then we've got the pressure gauge right here, if we know there's, 2 feet of water, now I don't think that is actually what the numbers come out to be, but if it were 2 feet, you would know that you had a volume of water that was 3.86 feet by 3 feet by, let's just call that H, by whatever H is. And then you can convert that into gallons. Okay? So that's how that's going to work. As long as that tank has a consistent cross-sectional area that doesn't change, you can figure out the height and find the volume of the tank. And if you got the pressure,
The pressure's not given?
it is. It's I think I asked for 2468 psi. I think.
No.
Oh, I didn't.
I see no.
Just PSI readings.
Oh yeah, there we go. PSI readings down there.
Yeah.
See, it's on the sketch down below, on the lower right.
Oh, that's just the.
So you're changing that over to 4 reading?
Yeah. So I'm just asking you, instead of that gauge reading 2, 4, 6, and 8 psi,
How many pounds would that equal?
or how many gallons?
Per gallon.
Yeah. Okay. So that's what I'm doing there. Okay. So you got, and you see it right here, 2468. So you got PSI, probably go to feet, then probably go to cubic feet, and then probably go to gallons. That's basically how I do that, okay? Just walk it on across. And that's how these things work. I mean, you just find the pressure, convert that to a height, and then you know the cross-sectional area, you can get the volume, and then convert that. Usually into gallons is what we use in this country. Yeah, it's a fair number of gallons in there, yeah. It's an even, they're even numbers, I'll tell you that, yeah. So, the numbers on the face of the gauge on the right, the gallon readings ought to be pretty even. Okay. So we good with that? Okay. Okay, the next two are those the vacuum kind of problems. Okay, and I think I put the table right on there for you on the first one. You'd use the table again for the second. So we got 12 inches of mercury vacuum. So what I'd do there, I'd look at the mercury vacuum right there. And so what we're doing here is we are drawing a horizontal line across at 12 inches of mercury vacuum. And then we're going to find the readings that go to the line for the different units. So PSIA, okay, that's perfect vacuum, atmospheric pressure. Here's PSIA, so that's going to come up like so. All right, and then we got a water barometer. That would do that, like so. And then we've got water vacuum. Let's see. So water vacuum would be right here. So you just want to pay attention to which side of the line you're on, you know, as you go through these. And you just figure out, looks like I forgot one. So I'll get that last one there, that one on top. The mercury barometer, there we go. You start at 0 and you measure to the line. So we've got something going on like that, okay? All right, so what you would do then is you would say, okay, I got 12 inches of mercury vacuum, mercury vacuum. So how much of the scale does that take up? So I've got 12 inches of mercury. The total is 30. So when I divide that out, I get 12 over 30, and that comes out to be 0.40, I think. So what that means is I've got 40% of the scale above the yellow line and 60 below. So I've got 40% above and 60 below. So once you've got that, you can just start calculating how much of, you know, for each unit system, what the different values would be. Now, the two things to remember on this is you always start at 0 and measure from 0 to the line, and then you just want to go ahead and convert the different units. I mean, that's basically what you're doing. So we've got 60% of the PSI A to go from 0 up to that line. The total is 14.7. So if you take 60% of 14.7, you'll get the reading for that, for the PSI A, which starts at 0 on the bottom and goes up. All right, so that's 8.82. Okay. And yeah, you can just kind of work your way through that. You got 40% for the water vacuum and 60% for the absolute pressure, the mercury barometer, and the water barometer. And then 40% for the water vacuum. Okay, are you okay with working through those? So for that water vacuum there, it's 40% of 34. The mercury?
Yeah.
Yeah, it does.
Then if it's 12% for the, or 12 inches for the mercury, wouldn't the mercury 40% on the water and 60 on top?
Okay, now there's two kinds of mercury. There's a mercury barometer and a mercury vacuum.
Gotcha.
And so, you know, they got different 0 points. So every one of these has two different 0 points you can use. So,
Well, that's what I was looking at. It's like, you're right, I'm doing my favorite trick of being fun the way you don't.
yeah, okay, there we go, yeah. Yeah. But that is the thing on this, is there's lots of ways to measure these things, you know. So, okay with that. And keep in mind that I've got that chart on your blue formula sheet, okay?
That's what I was looking at, and I looked at the very front and said mercury and didn't look at the back.
Yeah, there we go, yeah. And so every one has two. Mercury's got two readings. Water does, and so does the PSI. Okay. So, got any questions on that one? Or the one that follows? They're all kind of on the same vein. Okay. Good with that? Okay. Okay, the last one's this one. Now these are, like I said, you're the first class I've asked where no one has seen one of these, so maybe the time for this problem is running out, but we'll still go over this in a little bit, okay? So what you do is you look at what is different about the two situations. You've got two pipes, and even though they just look like circles, they're actually 3D. I mean, they're pipes is what they are, okay? And okay. And so what the one on the left is pushing water toward, or excuse me, pushing mercury towards the one on the right. And the thing you want to remember is the one on the right is actually pushing a little bit of water towards the one on the left. The one on the left is the stronger of the two, okay? Because it's pushing the heavier fluid, which is mercury. Okay. Now our conversions are all set up for feet, so I'll take that 14 inches and go 1 foot to 12 inches, and I'll convert that into feet. It's 1.167 feet, okay? All right, and then what you want to do is you want to look at the mercury. Now the chemical symbol for mercury is Hg. For some of those metals like gold and silver and mercury, I don't know if there's any others, but we use the chemical symbols come from like Greek and or Latin names, I think it is. So that's why they're kind of funny, okay? So for Hg, what you've got there, you got 1.167 feet. You know that you got 0.433 psi per foot, and then you know that mercury is 13.6 times as heavy as water. So based on that, you can come up with a pressure, okay, and that's 6.87 psi, okay. But you've also got water, okay? And you have to remember that that's what the pipe on the right is doing. It's pushing water up towards the one on the left. And that would be a negative, so that's negative 0.5, we'll call it 0.51, okay? So what you're looking for is the difference between the two for your answer. So we're doing all right with that? And that's called a YouTube manometer. The things I remember being in those things is there was mercury. And they might have used that in wastewater plants. Of course, they wouldn't have that anywhere near a water plant, but they use those in wastewater plants. And then there's also this red oil they used to use, and I'm not quite sure what the heck it was, but I remember that, seeing that years ago in some of these manometers too. I think I've even seen it in thermometers, if I'm not mistaken. Cheaper ones. Anyway. Yeah, I don't know what it is, but it was red. It was kind of a bright red color. That's what I remember. I don't know what it was. Okay, so we doing all right with that? This stuff? It's due Monday. Okay. All right. All right. All right. right, so we're on to the next one here. So we've done specific gravity and density and that kind of thing. And then we just did pressure. Now the next little step here is force, which is just an extra step beyond pressure, you might say. Okay, so we've got different forces that we deal with here. You know, if you're going to design the footing for that water tank, you want to know how much force it exerts downward, which otherwise is known as the weight. Okay. And then another thing you got going on here, a little harder to see maybe, but down by that arrowhead for force is a hatch, right? And see, there's a little something going on with that too. There's fluid pressure pushing on that hatch that creates a force trying to tear the lid off. So you got to attach that lid on pretty strongly. You know, when you build pipes, you use thrust blocks to absorb force. And I've heard a few stories of people neglecting to do these things and running into some problems. That's a thrust block there, just a big old chunk of concrete that helps hold that water T in place. Because when you have an unbalanced situation like that, like instead of a cross, you got a T, you're going to build up pressure that way. And well, that was interesting. Oh, okay, I see. So we have a unbalanced pressure pushing that way. And if you just let it sit there, you know, eventually that pressure might cause some leaks and things, okay? So you put that concrete block there to absorb that force that's being exerted by the water pressure on that back pipe. Okay? So those are just some examples of some of the forces we run into. Okay. So let's kind of start with the basics, and then we'll kind of go from there, like, you know, what we do here. So what we got here is we've got a water tank. Now for a water tank, the weight of the fluid inside is equal to the force. That's one way to find the force. So if we want to design that footing, we want to know what the force is. To find the force, one way to do it is to find the weight, okay? So to find the weight, we just find the volume of the container and then multiply it by the density of water, which is 62.4 pounds per cubic foot. I mean, that's about it. So what do we got here? Why don't you all find the area on that and then get the volume. Just stay in cubic feet on this thing because we've got the density of water 62.4, so we might as well just stay in cubic feet. So see, to get the volume and the weight in there, start with the area, pi r squared. You know, for a cylinder, what you do is you take the area that you've got, and that's, of course, this circle up here. So that, and then you take that, you multiply it by the depth of the tank. That's the general formula for doing volumes, is you take area, a constant area, times the depth, which I'll show in red there. That'll get you the volume. It's an area of a circle, so it's pi r squared. Now remember, circular things we usually call out by diameter. You'd probably want to use, you want to use the radius, which is half the diameter for your pi r squared. Okay. Okay, and then once you got that, just factor it up by 62.4 pounds per cubic foot. And you'll probably get a pretty large weight. So what they do when they build those footings under things is they look at how strong the soil is. You know, soil's like anything, it can bear so much pressure, basically. So you look at that and then just make sure you're spreading out the load enough so the soil can hold it without being crushed.
You doing all right on that? Yeah. Okay. I see that.
Everybody good on that? Get the volume. Now you might round a little different. You know, who cares? If you got something around 1,700,000 and some thousand pounds, if your number's a little different than mine, you know, it's fine. We're not going to design a different footing just because I got 1,764,318 and you got 1,764,302. I mean, we're going to design the same footing. You know, it doesn't make any difference. Don't worry about a little difference like that. Okay. We okay with that? All right. Now that's probably how I would do this. I mean, if I were doing a footing, I just get the weight, but there's another way to do it too if you want. And the other way to do it is to work with the pressure formula, okay? Because we got F, the force. Well, let's see what we got there for the so what we have there for the pressure formula is it's equal to force over area. Well, you can solve it for force. It's pressure times area. So that's the other way to do these problems.